But I guess Jeremy, for the past 5 years, has been working on aerospace engineering and air traffic control problems at NASA, kind of combining the two. So I really look forward to hearing from him today. So welcome, Jeremy.
As was mentioned, I'm Jeremy Coupe from NASA Ames, right down the street. And today we'll be talking about some of the work we're doing on what we call our machine learning airport surface model. Okay, so the kind of outline for today's talk here is we're going to start off by describing the operational problem that we're trying to solve. We'll talk a little bit about how we're delivering decision support to human users of the system through what we call this digital information platform. We'll get a little bit more into the details of the underlying machine learning airport surface model. And then ultimately, this is a system that is not fully automated, and there's human in the loop that are trying to kind of make the best decision. So we'll talk a little bit about the considerations, given that there are human in the loop in this kind of process, and then we'll finish with some kind of conclusions. But we'll start with the operational problem here. Sorry, a little delay, but we'll get through it. Okay. So here is really kind of a cartoon image that describes the problem that we're trying to solve. So on the left-hand side is an illustration of the problem. And the way maybe to think about this is through an analogy, which is like Google Maps or Waze. And so the idea here is when you're driving to work, you can get in your car, you have a destination that you want to go to, you pull up Google Maps, and there's a preferred route that you'd like to drive, and you typically would drive that route. However, some days there might be an accident or congestion, and there's these alternative routes that might be longer, but if they avoid congestion or delay, they'll actually get you to your destination quicker. So that's what we have here on the left-hand side, kind of illustrates the problem. Here we're showing individual aircraft, but really those aircraft represent airports. And then all these airports are within a single, what we call TRACON environment or metroplex. And all these airports are sharing these common resources, which are those 16 dots along the edge of the square, which represent departure fixes, which is kind of like a route structure the flight has to fly through. So what can happen is you have all these airports sharing these common resources, and as you see here, weather rolls in, and in response to the weather, air traffic controllers put restrictions on the system. So here we're showing restrictions in the form that 3 of our 4 departure fixes out that top departure gate are closed, and all the demand that usually would go through all those fixes is routed to the one remaining departure fix that's open, shown there in green. What happens here is you have this demand capacity imbalance along the terminal boundary, and delay starts to propagate back from the airspace onto each individual airport surface within that terminal environment. So the solution here is shown on the right, which is oftentimes, even though you have this demand capacity imbalance along one piece of the airspace, there is available capacity in other portions of the airspace. So what flight operators do is they provide to us what's called a trajectory option set, which is a set of alternative routes that they're willing to fly. And then we start generating predictions of delay on both the original filed route and all these alternative routes. And when the delay savings kind of exceeds some threshold value, we would say that that route becomes a candidate for reroute. And then we would recommend that to the flight operators. So that's the operational problem that we're trying to solve. But like I said, it gets very complicated because it's not just a matter of us generating quality predictions. We're doing this within a safety critical system with humans in the loop. And so it's really about the process, procedures, and workflow that makes this a very complicated kind of system altogether. So here we'll talk a little bit about the workflow, which is, well, we begin by pre-configuring the system. For this talk, that probably think about we're training all of our machine learning algorithms. Then the system is running in the background, and it's monitoring this demand and capacity. Again, it's generating predictions of delay on both the filed routes and all the alternative routes. Here is where we get the first human in the loop. So even though the system might detect some route is a good candidate for reroute, it's not going to automatically put the flight on that route. It's going to recommend a reroute to the flight operator. So here, this little orange human represents a flight operator. Think about American Airlines, Southwest Airlines, etc. The human looks at this, prediction and will evaluate if they want to submit that flight for a reroute or not. Now, if American Airlines says this is a great opportunity to reroute, let's reroute. They'll submit that reroute to air traffic control. And then this is where the second human is in the loop in this process, is air traffic control gets the reroute request. They have to evaluate if it's safe, if it kind of conforms with everything that they are expecting in the airspace, and they will either accept or reject that reroute. And then in the background, our system is generating predictions and generating a lot of data that we use for evaluation, post-operational analysis, and also benefits assessment. So the really interesting thing here is that this system, this workflow that I described here, is not just something that we use to write papers. We built and deployed this operational system in North Texas. So here you're seeing our field demo partners in North Texas. We're running at American Airlines, Southwest Airlines, Envoy Airlines operational control centers. We're also running tools at a handful of FAA facilities here in North Texas. And one of the key things here to, I think, notice is that you have this complicated process that is a combination of predictions, humans, and then coordination between flight operators and air traffic controllers. And so how do we actually enable all this coordination is that in each one of these facilities that you see, even though they're geographically distributed all over the place, we have deployed a NASA user interface that enables the humans to see our predictions and then also coordinate with each other to kind of enable this workflow that we talked about. And so that's kind of one of the unique pieces here as well, which is, again, that we're not just generating predictions, we need to enable the coordination and the workflows. And so here just quickly is to show like what our user interface looks like. We don't have to get too much into the details here, but on the left-hand side is what is our timeline. So each little flight here is shown at the predicted takeoff time. The right-hand side is the east runway. The left-hand side is the west runway. We have visuals of both the airspace and restrictions in the top middle. We have visuals of the airport surface in the top right. And then that table that you see along the bottom right is really where we kind of deliver many of the predictions and critical data elements that alert flight operators to these reroute opportunities. So we talked about the operational problem. We talked about that we're kind of enabling it through this NASA user interface that is deployed to all these different facilities. But how do we actually deploy this user interface? And here we'll get into a little bit of kind of the underlying infrastructure that enables not only all these cloud-based predictions, but then delivery of the interfaces to the users in the field. So here's kind of a cartoon image of what NASA calls our digital information platform. And this isn't necessarily the topic of the talk, so I won't go too deep, but suffice it to say that if you look at the bottom right, you'll notice there's these data sources. So in aviation, you have oftentimes all these kind of independent data sources, and there's a need to kind of mediate and fuse those data sources into a simplified single data feed that then you can kind of use throughout a system. So we have all these disparate data feeds we fuse together, and then we make that fused, simplified data feed available via this common platform. Once you have the fused data feed available to you, you can start to build all these different services on top of the foundational layer of data. That's kind of what the building blocks in the middle represent, is each little kind of service in maybe a service-oriented architecture. And then ultimately, right, you can have all these services that build on top of each other, and you can get a more sophisticated capability like the predictive engine we've talked about here. But then ultimately, what this also enables, this cloud-based digital information platform, is that we can deliver decision support tools to the users via this digital information platform and enable these front-end applications that you see here. So, we talked about the operational problem, which again is these kind of like pre-departure reroutes, which are very analogous to Google Maps or Waze, trying to find the best route to get to your destination. We enable this and deploy it via NASA's digital information platform. So what about the actual machine learning? We haven't talked at all yet really about machine learning. So let's get into a little bit about the kind of predictive engine under the hood. If we were to go into more details about the problem we're trying to solve, this is again kind of an illustration of the technical problem we're trying to solve in the Metroplex environment. So the Metroplex environment is analogous to this volume on the left, where you have multiple airports. They're sharing these common resources in the airspace. And ultimately, you can see here, or maybe imagine, that this is a complicated problem. And we need to generate a coordinated schedule that accounts for both the arrivals, the departures, and the surface traffic. And this can be challenging because anytime you deconflict an aircraft in the airspace, well, maybe that generates a conflict on the surface. And now you have to deconflict at the surface, but maybe it comes back and generates a conflict in the airspace. So you have to have these coordinated schedules that account for this whole holistic arrival, departure, surface traffic, and they have to comply to all known constraints in the system. And with air traffic, you have many, many constraints in the system. So how do we do this? Well, there's some color missing here, but suffice it to say that we apply this scheduling algorithm. The scheduling algorithm is really a three-step process. The first step of the process is we do what's called model the unimpeded trajectory. So we start with a trajectory that kind of makes an assumption there's no other traffic in the airspace. Once we have unimpeded trajectories for all the aircraft, we use those as input to our scheduling, which is really the second step of this process, where we schedule all the flights on their filed routes. Then the third step of this process is, well, there's all these alternative routes, so let's schedule on the alternative route so we can start to get a delta between delay on the filed route and the alternative route. And what we found is that, we deployed this system in Texas, but we wanted to scale to many other airspaces, but our solution had a bottleneck. And that bottleneck was the modeling of the unimpeded trajectory. When we go to the scheduling component of this process, it's actually relatively scalable, but in order to model the unimpeded trajectory, why is it the bottleneck? It's the bottleneck because it requires a significant amount of adaptation. Now, what do we mean by adaptation? Here is an illustration of what we mean by adaptation. So for each airport and also the airspace in general, we needed effectively detailed blueprints of the airport. We needed then to generate a link node network on that airport. Once you generate a link node network, you can have a trajectory from the gate to the runway, and you know kind of the route it's going to take. You can propagate it at a particular velocity, and you could say, great, going from gate A to runway X takes 3 minutes, 14 seconds, and you have your unimpeded trajectory. That's great, but it requires a significant amount of time and effort to develop this adaptation, and not only to develop it, but then also to maintain it. And so if we wanted this capability to go from Texas to many different locations across the country, this just wasn't a very practical approach. So now, 15 minutes into the talk, we finally get to the machine learning, which is, well, we had this challenge that we needed to generate an unimpeded trajectory, which we would use as input to our scheduler. And we said, okay, well, can we, make a scalable solution by replacing this legacy adaptation-based, physics-based surface model with a machine learning airport surface model? So what we did is we kind of identified the critical data elements that were needed by our scheduler to come up with that coordinated schedule. And we instead of having this physics-based model that generates these critical data elements, we learn directly from the data. And then we can start to generate things like predictions of runways, predictions of these unimpeded taxi times, predictions of airport configuration, which is like, is the airport flowing in a north flow or a south flow or vice versa. So here is really the kind of now new foundation of our predictive engine that generates these reroute recommendations, which is this machine learning airport surface model. So as I said, for us, the machine learning airport surface model was not necessarily about building a new system that is 10x more accurate than the old system. It was all about scalability for us. So we wanted to replicate the performance of our physics-based models. They were very, very good at what they did. They just weren't scalable. So for us, we kind of make the analogy that the physics-based airport surface model is like a skilled worker. It can do one thing very, very good, but if you needed to build 100 widgets, it's just not the person that you go to. In the analogy, the machine learning is more like a 3D printer, where all of a sudden, if you have to build 100 widgets, the machine learning is a much more attractive approach. So quickly, we'll get here into the last part, which is the human in the loop considerations, because again, this is not just a fully automated system. There's humans on both ends of the recommendations that they need to kind of coordinate with each other. So what type of special considerations do we have to make with the machine learning airport surface model, given that there's humans in the loop? Well, what we learned is, that, okay, this machine learning airport surface model is the foundation of this predictive engine. This predictive engine is being monitored by both flight operators and air traffic controllers. But what we learned here, is that air traffic control views one of these data elements as their job, as their function, and that's the departure runway. Why is it their job? Because as demand is coming for an upcoming, period of time, air traffic controllers are trying to do what they call load balancing across the departure runways, so that you don't have all the demand on one departure runway while one is sitting there completely empty, or vice versa. So they look at the demand over, say, the next hour. They do a mapping of the departure fixes to the runways in such a way that they can balance that demand. So it's really their function or their job to assign aircraft to runways. And so the problem here is that, well, our machine learning can also predict the runway. It actually can predict it with about the same level of accuracy as the air traffic control assignments. However, it's not appropriate for us to override their mental expectations of how traffic is going to flow. And the reason is because, effectively, imagine air traffic control expects some aircraft to take off on the west runway, and our system puts it on the east runway. And American Airlines says, hey, I want to reroute this aircraft from east to west. Air traffic control gets that request. They say, this aircraft's already on the west runway. Why are you wasting my time? Why are you driving up my workload? And it's just not an acceptable solution to air traffic control to be bothered with these predictions that don't align with their mental expectations. So what did we do? We gave air traffic control a knob. And air traffic control, with this knob, can define the load balancing strategy across the runways. And now the traffic flows for the distribution of departures to runways matches their mental expectation. And then now we don't get in a situation where the models are kind of conflicting with their expectation of traffic flows. So now we'll finish this off with conclusion and then be available for questions. So in conclusion, these pre-departure reroutes can be an effective tool to reduce delays on the airport surface. We provided decision support tools to both flight operators and air traffic controllers via this NASA digital information platform. The machine learning was not about making a model that was way more accurate than our legacy physics-based models. It was about providing a scalable solution for the underlying predictive engine. And then ultimately, the machine learning airport surface model is a combination of both machine learning predictions and human input to make sure that we match ATC expectation of traffic flows and don't kind of conflict there. So that was the end, and happy to take any questions.
Okay, thanks, Jeremy. That was amazing. Honestly, when I see systems like that, I'm just amazed at the complexity we already have in the world, and I don't know why we keep making more. So, does anyone have any questions they want to ask? We have time for a few here. I guess not. Oh, I guess there's one in the back.
Yes, thank you for your presentation. So I see that we have like some questions about the difference between the decision support, because we see that there are many applications of the machine learning into the decision support system for the human to get the final decision. So what is the difference between that to the ML airport surface that combine the human input with the expectation of the ATC controller? Because it's kind of like very similar to the procedure, right?
Yeah, so I'm not sure I understand it. You're asking what's the distinction between a generic decision support tool and our machine learning airport surface model?
Yes.
So I would say our machine learning airport surface model is, it's intended to be a decision support tool. And so all this is being fed to the human users, which then are still in control of the decision. And then and as we mentioned though, it's not just a single decision, it's actually this coordination of decisions between flight operator and air traffic controller. But ultimately, in air traffic, it's still a very human-centric function. And so we're never gonna, some people in NASA might disagree, but you know, like our path to getting to a fully automated system is not so clear. So all of our tools are intended to be decision support.
Thank you.
Okay, we have one over there.
Thanks again, very exciting. In terms of uncertainty quantification or assessing the certainty or confidence of machine learning predictions, there has been a lot of work in terms of trying to say something about how confident the model is. From your experience, I'm sure you have seen that with users in the loop. You see lots of value for adding a certainty or a confidence metric with the prediction, or is that something that users don't quite like to see?
That's a great question. So this is actually probably one of NASA's first tools that is in the hands of the users, that we generate a probability that the delay savings will be achieved. And the users actually quite like this. So we have all this historical data that tells us about how accurate the system is. So in the context of that historical accuracy, we can say things like, well, if we predict 23 minutes of savings, the probability you'll achieve greater than 10 minutes is X, Y, or Z, right? And so we've always wanted to put probabilities more into the hands of the users, because as scientists, we're like, hey, this is really cool, right? But this was the first one that they really started to appreciate it. And then moreover, we're working with Southwest Airlines as a partner, and they're actually starting to ask more and more for probabilities, because they want to put it into a decision-making framework that weights things by the probabilities. So if you have all these different discrete outcomes, you assign probabilities to them, now you can start to make informed decisions across that. And so yeah, I think that it's exciting to see this kind of introduced. In air traffic, the place actually that it's that NASA doesn't develop these tools, but MIT Lincoln Lab does, is in weather. And then there's all this stuff about like weather cells and the probability that a pilot would be willing to fly through a weather cell. And so then they have these like probabilistic forecasts about how willing pilots would be to kind of fly through different weather.
Okay, thank you so much, Jeremy.
Thank you.